Rheology is the study of the flow of matter, primarily in a liquid state, but also as soft solids or solids under conditions in which they respond with plastic flow rather than deforming elastically in response to an applied force. It applies to substances which have a complex microstructure, such as muds, sludges, suspensions, polymers and other glass formers, as well as many foods and additives, bodily fluids and other biological materials or other materials which belong to the class of soft matter. Newtonian fluids can be characterized by a single coefficient of viscosity for a specific temperature. Although this viscosity will change with temperature, it does not change with the strain rate. Only a small group of fluids exhibits such constant viscosity. The large class of fluids whose viscosity changes with the strain rate are called non-Newtonian fluids. Rheology generally accounts for the behavior of non-Newtonian fluids by characterizing the minimum number of functions that are needed to relate stresses with rate of change of strain or strain rates. For example, ketchup can have its viscosity reduced by shaking but water cannot. Ketchup is a shear thinning material, like yogurt and emulsion paint, exhibiting thesotropy, where an increase in relative flow velocity will cause a reduction in viscosity, for example, by stirring. Some other non-Newtonian materials show the opposite behavior, riː_ɛlādʒi, viscosity going up with relative deformation, and are called shear thickening or dilatant materials. Since Sir Isaac Newton originated the concept of viscosity, the study of liquids with strain rate-dependent viscosity is also often called non-Newtonian fluid mechanics. The term rheology was coined by Eugene C. Bingham, a professor at Lafayette College, in 1920, from a suggestion by a colleague, Marcus Reiner. The term was inspired by the aphorism of Simplicius, Panta rhei, everything flows. The experimental characterization of immaterials' rheological behavior is known as rheometry. Although the term rheology is frequently used synonymously with rheometry, particularly by experimentalists, theoretical aspects of rheology are the relation of the flow, deformation behavior of material and its internal structure, and the flow, deformation behavior of materials that cannot be described by classical fluid mechanics or elasticity. Scope. In practice, rheology is principally concerned with extending continuum mechanics to characterize flow of materials that exhibits a combination of elastic, viscous and plastic behavior by properly combining elasticity and fluid mechanics. It is also concerned with establishing predictions for mechanical behavior based on the micro or nanostructure of the material, e.g., the molecular size and architecture of polymers in solution or the particle size distribution in a solid suspension. Materials with the characteristics of a fluid will flow when subjected to a stress which is defined as the force per area. There are different sorts of stress and materials can respond differently for different stresses. Much of theoretical rheology is concerned with associating external forces and torques with internal stresses and internal strain gradients and flow velocities. Rheology unites the seemingly unrelated fields of plasticity and non-Newtonian fluid dynamics by recognizing that materials undergoing these types of deformation are unable to support a stress in static equilibrium. In this sense, a solid undergoing plastic deformation is a fluid, although no viscosity coefficient is associated with this flow. Granular rheology refers to the continuum mechanical description of granular materials. One of the major tasks of rheology is to empirically establish the relationships between deformations and stresses by adequate measurements. Although a number of theoretical developments are also required before using the empirical data, these experimental techniques are known as rheometry and are concerned with the determination with well-defined rheological material functions. Such relationships are then amenable to mathematical treatment by the established methods of continuum mechanics. The characterization of flow or deformation originating from a simple shear stress field is called shear rheometry. The study of extensional flows is called extensional rheology. Shear flows are much easier to study and thus much more experimental data are available for shear flows than for extensional flows. Rheologist. A rheologist is an interdisciplinary scientist or engineer who studies the flow of complex liquids or the deformation of soft solids. It is not a primary degree subject. There is no qualification of rheologist as such. Most rheologists have a qualification in mathematics, the physical sciences, engineering, medicine, or certain technologies, notably materials or food. Typically, a small amount of rheology may be studied when obtaining a degree, but a person working in rheology will extend this knowledge during postgraduate research or by attending short courses and by joining a professional association. Viscoelasticity. Fluid and solid character are relevant at long times. We consider the application of a constant stress. If the material, after some deformation, eventually resists further deformation, it is considered a solid. If, by contrast, the material flows indefinitely, it is considered a fluid. By contrast, elastic and viscous behavior is relevant at short times. We again consider the application of a constant stress. If the material deformation strain increases linearly with increasing applied stress, then the material is linear elastic within the range it shows recoverable strains. Elasticity is essentially a time-independent process, as the strains appear the moment the stress is applied, without any time delay. If the material deformation rate increases linearly with increasing applied stress, then the material is viscous in the Newtonian sense. These materials are characterized due to the time delay between the applied constant stress and the maximum strain. If the materials behaves as a combination of viscous and elastic components, then the material is viscoelastic. Theoretically, such materials can show both instantaneous deformation as elastic material and a delayed, time-dependent deformation as in fluids. Plasticity is the behavior observed after the material is subjected to a yield stress. A material that behaves as a solid under low applied stresses may start to flow above a certain level of stress, called the yield stress of the material. The term plastic solid is often used when this plasticity threshold is rather high, while yield stress fluid is used when the threshold stress is rather low. However, there is no fundamental difference between the two concepts. Applications. Rheology has applications in materials science, engineering, geophysics, physiology, human biology and pharmaceutics. Materials science is utilized in the production of many industrially important substances, such as cement, paint, and chocolate, which have complex flow characteristics. In addition, plasticity theory has been similarly important for the design of metal-forming processes. The science of rheology and the characterization of viscoelastic properties in the production and use of polymeric materials has been critical for the production of many products for use in both the industrial and military sectors. Study of flow properties of liquids is important for pharmacists working in the manufacture of several dosage forms, such as simple liquids, ointments, creams, pastes, etc. The flow behavior of liquids under applied stress is of great relevance in the field of pharmacy. Flow properties are used as important quality control tools to maintain the superiority of the product and reduce batch-to-batch variations. Materials science polymers examples may be given to illustrate the potential applications of these principles to practical problems in the processing and use of rubbers, plastics, and fibers. Polymers constitute the basic materials of the rubber and plastic industries and are of vital importance to the textile, petroleum, automobile, paper, and pharmaceutical industries. Their viscoelastic properties determine the mechanical performance of the final products of these industries, and also the success of processing methods at intermediate stages of production. In viscoelastic materials, such as most polymers and plastics, the presence of liquid-like behavior depends on the properties of and so varies with rate of applied load, i.e., how quickly a force is applied. The silicone toy, silly putty, behaves quite differently depending on the time rate of applying a force. Pull on it slowly and it exhibits continuous flow, similar to that evidenced in a highly viscous liquid. Alternatively, when hit hard and directly, it shatters like a silicate glass. In addition, conventional rubber undergoes a glass transition, e.g., the Space Shuttle Challenger disaster was caused by rubber O-rings that were being used well below their glass transition temperature on an unusually cold Florida morning, and thus could not flex adequately to form proper seals between sections of the two solid-fuel rocket boosters. Biopolymers sol-gel with the viscosity of a sol adjusted into a proper range. Both optical quality glass fiber and refractory ceramic fiber can be drawn, which are used for fiber optic sensors and thermal insulation, respectively. The mechanisms of hydrolysis and condensation, and the rheological factors that bias the structure toward linear or branched structures are the most critical issues of sol-gel science and technology. Geophysics includes the flow of molten lava and debris flows. Also included in this disciplinary branch are solid earth materials which only exhibit flow over extended time scales. Those that display viscous behavior are known as rheōs. E.g., granite can flow plastically with a negligible yield stress at room temperatures. Long-term creep experiments indicate that the viscosity of granite and glass under ambient conditions are on the order of 10-20 poisers. Physiology includes the study of many bodily fluids that have complex structure and composition, and thus exhibit a wide range of viscoelastic flow characteristics. In particular, there is a specialist study of blood flow called Rheology. This is the study of flow properties of blood and its elements. Blood viscosity is determined by plasma viscosity, hematocrit and mechanical behavior of red blood cells. Therefore, red blood cell mechanics is the major determinant of flow properties of blood. Food rheology is important in the manufacture and processing of food products, e.g., cheese. Thickening agents, or thickeners, are substances which, when added to an aqueous mixture, increase its viscosity without substantially modifying its other properties, such as taste. They provide body, increase stability, and improve suspension of added ingredients. Thickening agents are often used as food additives and in cosmetics and personal hygiene products. Some thickening agents are gelling agents, forming a gel. The agents are materials used to thicken and stabilize liquid solutions, emulsions, and suspensions. They dissolve in the liquid phase as a colloid mixture that forms a weakly cohesive internal structure. Food thickeners frequently are based on either polysaccharides or proteins. Concrete rheology. Concretes and mortars workability is related to the rheological properties of the fresh cement paste. The mechanical properties of hardened concrete increase if less water is used in the concrete mix design. However, reducing the water to cement ratio may decrease the ease of mixing and application. To avoid these undesired effects, superplasticizers are typically added to decrease the apparent yield stress and the viscosity of the fresh paste. Their addition highly improves concrete and mortar properties. Filled polymer rheology. The use of various types of fillers incorporated into the polymer has become quite common as a means of reducing cost and to impart certain desirable mechanical, thermal, electrical and magnetic properties to the polymers. The advantages that filled polymer systems have to offer are normally offset to some extent by the increased complexity in the rheological behavior that is introduced by the inclusion of the fillers. Usually when the use of fillers is considered, a compromise has to be made between the improved mechanical properties in the solid state, the increased difficulty in melt processing, the problem of achieving uniform dispersion of the filler in the polymer matrix, and the economics of the process due to the added step of compounding. The rheological properties of filled polymers are determined, not only by the type of the filler, but also by its size, shape, size distribution and amount. A key factor in the use of fillers without affecting the material properties is the stress transfer at the filler-polymer interface. The interfacial adhesion can be substantially enhanced via a coupling agent that adheres well to both the polymer and the filler particles. The type and amount of surface treatment on the filler are thus additional parameters affecting the rheological properties of filled polymeric systems. Measurement. Rheometers are instruments used to characterize the rheological properties of materials, typically fluids that are melts or solution. These instruments impose a specific stress field or deformation to the fluid, and monitor the resultant deformation or stress. Instruments can be run in steady flow or oscillatory flow, in both shear and extension. In 1932, Fritz Hoppler got a patent for the falling ball viscometer, named after him, the worldwide first viscometer to determine the dynamic viscosity. Dimensionless numbers. Deborah number. On one end of the spectrum we have an inviscid or a simple Newtonian fluid, and on the other end, a rigid solid. Thus the behavior of all materials falls somewhere in between these two ends. The difference in material behavior is characterized by the level and nature of elasticity present in the material when it deforms, which takes the material behavior to the non-Newtonian regime. The non-dimensional Deborah number is designed to account for the degree of non-Newtonian behavior in a flow. The Deborah number is defined as the ratio of the characteristic time of relaxation to the characteristic time of experiment or observation. Small Deborah numbers represent Newtonian flow, while non-Newtonian behavior occurs for intermediate-range Deborah numbers, and high Deborah numbers indicate an elastic, rigid solid. Since Deborah number is a relative quantity, the numerator or the denominator can alter the number. A very small Deborah number can be obtained for a fluid with extremely small relaxation time or a very large experimental time. For example, Reynolds number in fluid mechanics. The Reynolds number is a measure of the ratio of inertial forces to viscous forces, and consequently it quantifies the relative importance of these two types of effect for given flow conditions. Under low Reynolds numbers, viscous effects dominate and the flow is laminar, whereas at high Reynolds numbers, inertia predominates and the flow may be turbulent. However, since rheology is concerned with fluids which do not have a fixed viscosity, but one which can vary with flow and time, calculation of the Reynolds number can be complicated. It is one of the most important dimensionless numbers in fluid dynamics and is used, usually along with other dimensionless numbers, to provide a criterion for determining dynamic similitude. When two geometrically similar flow patterns, in perhaps different fluids with possibly different flow rates, have the same values for the relevant dimensionless numbers, they are said to be dynamically similar. Typically it is given as follows, where us, mean flow velocity, ms-1, L, characteristic length, m, mu, dynamic fluid viscosity, nsm-2, or par s, nu, kinematic fluid viscosity, nu equals mu, rho, m squared s-1, rho, fluid density, kilogram m-3.